Welcome students to this video, and in this video we are going to talk about maximal principles. Now what are maximal principles? See, these are sort of theory. These are particular type of theory which we actually, so we call this sort of problems as a priori estimate. Okay, what is the a priori estimate? A priori estimate is essentially, given an equation. Yes, we do not know that whether that equation, let's say, has a solution or not. Okay, any equation doesn't really matter. Let's say y equals to 0. Okay, you do not have to know whether there is a solution or not. What we will do is we will assume that, let's say, that z, let's say, solves 1. Okay, now can we say something about z? What is the behavior of the z in the interior of points? How does it behave in the boundary? Let's say you are given that z satisfies this ly equals to 0, that equation, right? Now can you say that any solution of z has a maxima somewhere or a minima somewhere, right? That sort of questions maximum principles deals with. Essentially these are called a priori estimates, because without knowing the existence and uniqueness of solution, we derive some properties of the solution. A priori means beforehand. Okay, now you see, the thing is, and where is it important? Okay, now to be very frank with you, I really cannot tell you, emphasize enough how important this maximal principle is. Okay, you can, so uses, let's just put a small thing like uses, where you can use this thing. Although we are not going to do this in this course specifically, but you can use this to show existence and uniqueness. Or maybe I can show you, it's not a problem. Let me see if we can do that. Existence and uniqueness of solution. Okay, of solution. Okay, and you can also use it to look at the stability properties of the solution. Stability properties. Okay, properties. Okay, so this is very like a very important theorem, and to be very frank with you, this is probably the most important how do I put it, principle, most important theory which one can learn. So basically, given an operator, whatever the equation is, there is a corresponding operator, right? So given an operator, if you know what, if there is a maximal principle, your life becomes much easier. Okay, so what is the idea of the maximal principle? Basically that we are basically looking for a maxima or the minima, that sort of thing, of solutions. Okay, so without much ado, let me start with the theorem, and by explaining the theorem, I can better explain what exactly are we trying to achieve here. So let's say if y is in C2 alpha beta. What is C2 alpha beta? It is twice continuously differentiable functions defined on closed bounded interval alpha beta. Okay, so you are looking at a function y which is twice continuously differentiable in alpha beta, such that the function, the double derivative of the function of x, okay, this is always greater than equals 0. What does it mean? It means that the function is convex, okay, in open alpha beta. Double derivative is greater than equals 0 means it is a convex function, right? And yx attains its maxima, attains its maximum, okay, at an interior point, what is the interior point? Some interior point of alpha beta, okay. Then an amazing thing happens, yx is identically constant, in alpha beta. Okay, so beautiful theorem, right? So basically what it is saying is this: see, we are not really now basically, see, initially for this theorem we are not actually working with some equation or anything. We are just saying that you take any function, right? Doesn't really matter what is so equation it solves. It's just some function y which is twice continuously differentiable, such that it has to be convex. Y double prime x is greater than equals 0, convex. What it is saying is, if it attains a maxima at the interior point of alpha beta, yes, then it has to be identically constant in alpha beta. There is no other way. Is this okay? Right. So let's look at the proof of this. Proof. See that first of all, we will assume that let's say that y double prime of x is not greater than equals to 0 but strictly positive in alpha beta for now. Let's just assume that. Okay, so suppose y double prime of x is strictly positive in alpha beta. Yeah, you see why we can deduce something like this. Okay, now you see, let's say if yx, okay, attains its maxima in an interior, maxima at an interior, sorry, at an interior point, of alpha beta, then what can you say? Let's say, so basically what I'm trying to say is at an interior point of alpha beta, let's say x naught, and the point is x naught. Okay, then what can you say? Y prime at the point x naught has to be 0, right? Clear? Okay, and what can you say about double prime? Y double prime at the point x naught is less than equal 0. That's just the definition. The second derivative test, you know, right, that if it is a maxima at an interior point, it has to be critical point, so y prime x naught is 0 and y double prime x naught has to be less than equal 0. Yeah. Now see this, so basically you have a point x naught where it is less than equal 0, but we have assumed that y double prime x is positive. So that's a contradiction. That is a contradiction. Hence, what can you say? That if thus, what can we say? If y double prime of x is positive in alpha beta, then the function cannot attain its maxima at an interior point of alpha beta, at an interior point of alpha beta. Okay, I hope this is clear to you, that the thing is, it has to be, I mean, it has to be constant in that case. There is no other way. So y double prime x, if it is greater than 0, then it has to be constant. It cannot have a maxima at an interior point. Okay, it has to be everywhere. So basically same. Okay, now what happens if there are some points where it is 0, so the double derivative is 0. So now suppose y double prime at the point x is greater than equal 0, in alpha beta, and we will also assume that yx, okay, attains its maxima at x1, which is in alpha beta, open alpha beta, right, some point. Now if y at the point x1, is m, so what is the m? M is the maxima. Then what can we say? Then y of x should always be less than equal m. Okay, this is for all x in alpha beta. Okay, now you see what we will do is this: let there exist a x2, okay, which is between alpha beta, such that yx2 is less than m. Clear? So if x2 greater than x1, okay, so you see, if yx1 is equals to m, it means that the maxima is attained at the x1 point. So basically let's just assume that is m. So for any point x in alpha beta, y of x has to be bounded by m, right? That's what we wrote. Now let's just assume that there is a point where yx x2 is less than m. Of course, there has to be such a point. If there is no such point, then y will be a constant, right? It is identically equals to m and it's a constant, so we have already proved it. It's nothing to go on. Okay, so we'll assume that y of x2 is less than m. Clear? Okay, now once that is true, okay, so see, x1 is here, yeah, and now y of x2 is less than m. Y of x2 can be here, x2 can be here, x2 can be here, right? Let's say this is alpha, this is beta. Okay, now x2, we don't know where x2 is, but we know that there is a x2 such that y of x2 is less than m. Clear? Okay, then what we will do is this. So let's say x2 is greater than x1. So let's do x2 is here, not here, here, this case. Then we define a function, define z of x to be exponential gamma x minus x1 minus 1. Okay, what is the need of this function? See, basically what we are trying to do is this. We know that if y double prime is strictly positive for all x, right, then the maximum cannot be attained in the interior. We want to use this fact for the next part. So for next part, let's say we know that there are some points where it can be 0 also. Y double prime can be 0 also, right? So what we are doing is we are building a new function like this. So okay, and what happens is this. If you see, if we build z like this, okay, what we have is this. See, clearly z of x is negative for x in alpha x1. Clear? It has to be negative. See, x2 is greater than x1, right? And at the point x2, y of x2 is less than m. So basically, if you define this, you see, z of x, if you look at between alpha and x1, x minus x1, right? X minus x1. So in between this particular thing, this is basically negative, right? It is exponential gamma, some negative term, minus 1. So basically it is less than 1. So this has to be negative, right? Now, what is z of x1? Of course that is 0. See, z of x1, if I am putting, it is exponential 0. So is 1 minus 1. So basically 0. And if x is greater than x1, okay, so basically in that case, this is exponential of a positive minus 1. So basically you have this positive term, right? So you have, and z of x is positive for x in x1 beta. Is this okay? Also you see, this is important. Okay, z double prime, if you calculate of x, you see this is exponential gamma times things, right? So it is basically gamma square exponential gamma x minus x1 minus. Okay, so minus 1 is gone, right, with the derivative. Now this is positive. Exponential is a positive term, and gamma squared is positive. Okay, this is positive for all x in closed alpha beta. Okay, so now what we will do is this. See, this is a small trick which you are going to use just to, you know, I mean, get our result. Okay, so what we are doing is this. See, we got a z such that z double prime is positive. Yeah, now what we will do is we define a new function. Define w of x, which is y of x plus epsilon z of x. Okay, where this epsilon will specify here. You will see why we need this epsilon. Okay, so epsilon is positive and which is less than m minus yx2 by zx2. Is this okay? I mean, we'll define this new, and this epsilon is such that something like this happens. See, if this thing happens, what is the thing? So it becomes at the point x, w of x2. If we define epsilon like this, what happens to w of x2? It is y of x2 plus epsilon times z of x2, right? Z of x2 is, so this is strictly less than m minus y of x2 by z of x2. Okay, times z of x2. So this is gone. So this will be strictly less than m. You see, we are constructing this w in such a way that w at the point x2 should be always less than m. Why we are doing it, I will explain to you right now. Okay, so this is the reason why we are choosing a epsilon like this. Now, now since you see y of x2 is less than m, as I have explained, and z of x2 is positive. See, z of x2 lies between x1 and beta, right? So z of x2 is positive and y of x2 is less than m, because y, I mean, we have assumed this is our assumption, you see, this is our assumption. Okay, so therefore this sort of exists there, hence epsilon exists. Clear? Okay, and we also have that w of x is less than y of x. Okay, and which is less than equal m. Clear? For x in alpha x1 closed. See, between alpha x1, where is it? Here. Between alpha x1, z is negative. So basically, w will be dominated by y of x. Clear? And w of x2, we have just calculated it, right? W of x2 is strictly less than m. Yes. And what is w of x1? W of x1 is y of x1 plus epsilon times z of x1. Z of x1 is 0. So it is y of x1. Okay. Which is m. See, y of x1 is, what is it? Y of x1 is m. The maximum is attained there. Okay. So this is just a trick, because I want to use this particular thing, that a function, if it is strictly positive, then you know it has to be constant. This is what we need to use. Okay. Now see, since w double prime of x, what is it? It is y double prime of x plus epsilon z double prime of x. Okay, this is strictly positive in alpha x2 closed. Is it okay? Of course this is right. See, alpha x2, so it starts from alpha until x2, y double prime is given to be positive. We are assuming, you see, y double prime, we have assumed that y double prime x is strictly greater than 0. Okay, and what about this z? Z is such that z double prime is strictly positive, you see, between alpha and beta. Okay, here it is given z double prime is strictly positive. So y double prime x plus epsilon times z double prime x is strictly positive. Is this okay? And so in between alpha x2, what is happening is this: w double prime of x is strictly positive. Okay. Now since one second. Yeah. So we have actually found out a function which is strictly positive in alpha x2. Okay. So therefore the function, if you restrict it to alpha x2, w of x cannot attain okay, a maxima in the interior of alpha x2. Is it okay? Okay, it cannot have. This is where are we getting it? This we are getting from the first part. Right. Now let's look at it. See, the thing is, between alpha x2 we have it. Okay. Now you see, since what happens now, let's look at what happens at w and at the point alpha. W at the point alpha is less than m, right? This is what we calculated here. You remember? W at the point alpha is less than m, right? See, W at the point alpha is less than y at the point alpha, which is less than m, right? Okay, right. So W at the point alpha is less than m. W at the point x2 again is less than m, and W at the point x1 equals to m. Is it okay? See, W is such that, think about it this way. At the point alpha, this is x1, this is x2, x2 is here. This is what we assume, that x2 is bigger than x1. This is beta. W is less than M. So let's say this is your M, height is M. Okay, this is the M line. Okay, at the point alpha, W is less than M. At the point x2, W is less than M. So somewhere here, let's say, okay, here at the point alpha, here at the point x2, and at the point x1 it is equals to M. So basically it does this, right? Minimum, that's the minimum it had to do. Okay, so you see, then if it does, then Wx must attend a maxima greater than equals to M. Is it okay? At some point is taking M. So basically the maxima will be at least M, or it will be greater than equal M. It has to be in between alpha x2. Yes? I hope it is fine. At an interior point of alpha x2. See, between alpha x2 there is a point where it is taking at least M. At least, so basically the maxima is greater than equal M. Yes? Okay. So this is a contradiction, right? Because we just showed that Wx cannot attain any maxima in alpha x2. And here we are showing it is taking a maxima, it has to have a maxima between alpha x2. Okay. So that's a contradiction. Hence, what can we say? Hence, therefore, there does not exist a x2 between alpha beta. Clear? Between alpha beta, x2 greater than x1 such that y of x2 is less than M. Okay. Now what happens if x2 is less than x1? Then so if x2 is less than x1, we can do similar sort of analysis, but z of x we have to set a little bit differently. It will be exponential minus gamma x minus x1 minus 1. Okay, and you can do the similar sort of argument, and you can show therefore yx has to be identically equals to M in alpha beta. Is it okay? So basically what it is saying is this: if you have y such that it takes the maxima at an interior point and y double prime is positive, then it has to be identically constant. Please remember this thing. Okay, right. Now the thing is, so this is for any solution, any function, right? Doesn't have to be a solution or anything, it's just function. Okay, now you see, you can have the reverse inequality. So let me put a small remark here. One can have reverse inequality, okay, for minima. So what happens then? You can say that if you have a y which is C2 such that y double prime is negative, non-positive, essentially less than equal 0. Okay, then it will not be attaining its minima at an interior point. Okay, but and if it does, then it has to be constant. Is this okay? Now what we are going to do is look at some equations. We will use this and we will look at some equations from here. So first of all, see, the thing is, we want to generalize the idea. We want to use maximum principle. For what sort of problem? Let me write it down. Principle for this sort of problem: y double prime plus px y prime plus qx y is greater than equal 0. Is this okay? We want to write down a maximal principle for problems of this particular form. Okay, now you see, let me give you an example to show that one cannot expect something like that. So let's say that, you see, the function, let's say yx equals to sin x. Okay, we know that solves this equation, right? Solves y double prime plus y equals to 0. We know that, right? Okay, now in 0 pi, We know this, right? Yes. And where do you think the maximum is attained? The maximum is attained in the interior pi by 2, but maximum of y equals to y at the point pi by 2, right, which is 1. So it is attaining at the interior, right? So basically maximal principle, let me just write it, does not hold. Clear? So basically you cannot expect this. So basically, see, we did it for y double prime positive greater than equal 0. Now if you want to add some lower order terms, so basically y double prime plus py prime plus qy greater than equal 0, if you want to do similar sort of thing for this sort of equation, it does not work. That's what it says. Is it okay? Huh? But the thing is, but should we give up? But we should not. Huh? Let me will give you another example. See, let's say that b. You see, if you change the equation and then you have this sort of equation, let's say yx equals to e power x minus, let's say minus e power minus x, both are minus, minus e power x minus e power minus x. Solves this problem, right? Solves y double prime minus y equals to 0. Is it okay? And the maximum of y is attained at, if you can check it, it is attained at attained at 0, which is minus, attained at 0, which is minus 2. Okay. And this is also in minus 1 1. So basically it is not that only that particular equation has a issue. There are other equations also which you write, there are issues. Okay, so it can happen. Now the thing is this, but we can actually work around this problem. Okay, so we'll look at a theorem, and what does this theorem say? It says that let yx satisfies the differential inequality and di, let me just write it down, given by y double prime of x plus px y prime plus qx y, okay, greater than equal 0 for x in alpha beta. Here, where px and qx are non-positive and bounded. Positive and bounded. Please remember, non-positive and bounded, very, very, very important. We need these particular conditions, non-positive and bounded. Clear? Okay. In every closed subinterval of alpha beta. Okay, so I mean you can change boundedness to continuity also. It is not a problem. Then this will work. Okay, so basically you just assume that p and q are continuous, but they are non-negative. Non-positive. Yeah? Now, if yx assumes a non-negative maximum value m, okay, at an interior point of alpha beta, point of closed alpha beta, okay, then yx is identically equals to m. Okay, so we have the maximal principle. So what does it say? It says that if you look at this equation, y double prime plus px y prime plus qx greater than equal 0, and both are non-positive. So this is very important. P and q, they have to be non-positive. Okay, so it is less than equal 0 there, and they are continuous. For now, let's just assume it is continuous. You don't need continuity, but we can assume that. Yeah. Now you see, what it is saying is this, before we were not saying anything. See, before we just said that if the function attains its maxima at an interior point, it has to be constant. here we are not saying that. Here we are saying that if yx assumes a non-negative maxima, not any maximum but a non-negative maximum value m, okay, at an interior point, then it is constant. Is it okay? Right. So let's look at the proof. So you see, the thing is, let's just assume as we did it earlier, right? So first of all, suppose y double prime x plus pxy prime plus qxy, okay, is strictly greater than 0 in alpha beta. Let's just assume that. Okay. Now you see, we will also assume that and y attains a non-negative maxima. This is very important. Non-negative maxima, not any maxima but non-negative maxima. Non-negative maxima m. Let's say. So let us write it like this. Non-negative. So y be such that y at the point x naught equals to maximum of y, okay, here in alpha beta, okay, and what is it, equals to m, okay, so m will just, so let's say that is positive. This is what we are assuming. Is this okay? Then what we can say is this, see, then y at the point x naught, that will be capital M here, okay, and y prime at the x naught, this is maxima, this is a critical point, so it has to be 0. What happens to y double prime at the point x naught? If this is your second derivative test, maxima, so it has to be less than equal 0. Okay, so therefore y double prime at the point x naught plus p of x naught, y prime at the point x naught plus q of x naught, y at the point x naught. What happens to this? See, this term is not there because y prime x naught is 0. This is m times q. Okay, q is less than equal 0, right? It is non-positive. Q is non-positive. Y double prime is non-positive. So this is always strictly less than equal 0, right? That's a contradiction. Why contradiction? Because it is given that this is strictly positive. Okay, so it is a contradiction. Is this okay? So we basically have that if it is strict positive, then I mean there is something fishy going on, and we cannot have it have this assumption. So basically what it is saying is yx has to be strictly constant. So basically it's identically equals to m. Is this okay? Now let's look at the other part. What is the other part? If you know it is greater than equal 0, not just 0. So suppose y double prime plus p xy prime plus q xy, okay, let's say that this is greater than equals to 0, yes, and there is a x1 such that yx1 equals to m. So the maximum is attained at m for some x1 in alpha beta. Is it okay? And we suppose there exists a x2 in alpha beta such that y at the point x2 is strictly less than m. Yes, why? Because see, we are assuming, we are starting with the assumption this is not identically equals to m. So basically if that is not the case, there must be a x2, right, which at where y should be less than m. M is a maximum, it cannot cross m, so it should be less than m. Okay. Now again from the earlier thing, you remember, if let's say x2 is greater than x1, now we'll just use what we did earlier, same sort of ideas we will use it. So if x2 is greater than x1, then what we will do is we define a function z of x which is exponential, okay, gamma times x minus x1 minus 1. and gamma positive, of course, gamma positive, it is assumed to be determined, and you see the z of x, and z of x satisfies those conditions, right? What we did, earlier, that z of x is negative in alpha x1. You remember we just did it in the earlier theorem, z of x1, because it is basically the same function, right? Nothing changes, does not depend on the equation, and z of x is positive in x1 and beta. x1 and beta. Is it okay? Right. Sorry, it has to be closed beta, up till beta. Okay, so the z has that same property, it doesn't change anything. Now, since qx is negative, this is given non-positive essentially. Okay, it follows that, you see, z double prime plus px times z prime plus qx times z. Okay, what happens to this? Let's just look at it. You see, it is gamma square. If you just calculate it, yes, so please check this part. It is gamma square plus px times gamma plus qx, okay, 1 minus exponential minus gamma x minus x1, okay, and then exponential gamma x minus x1. Clear? That's what we are going to get. Okay, now this is always dominated by gamma square plus px times gamma plus qx times exponential gamma x minus x1. Is it okay? We can always do this, right? 1 minus exponential, so that is why we can show that this is always dominated by so this q can be replaced by this, right? Yeah. Okay, so now the thing is, you see, we choose, see, we have assumed that gamma is to be determined later, right? So we choose gamma such that gamma square plus p of x gamma plus q of x is strictly positive in open alpha beta. We can choose it, right? Gamma is some given function. Yes, gamma is nothing special. Gamma is some given function, so we can choose gamma such that gamma square plus px gamma plus qx is strictly positive. Okay. Now you see, if this happens, you see, gamma is such a function such that this is strictly positive, so that will give you that this is strictly positive times exponential, that is also strictly positive. So basically, therefore, z double prime plus pxz prime plus qxz will be strictly positive. Yes, we can do that. Now what we do is then we can say that, one second, I missed something. I don't think so. Yeah, this is fine, right? Yeah. So now if once this is positive, then this expression containing z, that is also positive. So we can use this particular thing, right? You see, if it is positive, if this expression is positive, then it has to be identically equals to m. If there is like if it assumes a non-negative maxima, that is okay. So we can use that, and then use the how do I put it? This part, yeah. See this logic which we used here. Okay, see, we showed that w double prime is strictly positive, and then it attains a maxima. Cannot attain a maxima. This you can say using the other part, the first part of the theorem, and this then you use this logic. Use this logic, exactly the same sort of logic works, and you show that it cannot work. I mean, the maxima cannot be attained. So basically you will get a contradiction. Okay, so use the same logic. Now what you do is, now use the same logic as in theorem 1 to arrive at a contradiction. I hope this is clear to you. Arrive at a contradiction. contradiction. Is it okay? Fine. So now the thing is, we can do what that we can do. You can use this actually theorems to actually prove some better results about solutions of some equations. That we will do. I will put some problems in the assignment where you will see that how maximum principle can be used to talk about uniqueness, or to give some sort of estimates, upper bounds or lower bounds on some solutions. So with this I am going to end this video.